A really big idea in combinatorics is the idea of a permutation. The word permutation just means an ordering. So if I'm counting permutations, that's like I'm counting how many orders are possible for something. Like how many ways can I put things in a sequence. So let's pretend I've got 10 books and 10 favorite books, my 10 favorite books. And I wanted to decide if I'm going to put them on my bookshelf like this. Here I've got my bookends. So here's all my books. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So how many different orderings could I put them on my bookshelf? You can think about this as a fundamental counting principle kind of a problem. Let's think about each of these possible slots as a position. So this is the position for book 1, this is the position for book 2, and so on. So in that case, you can ask, how many options do I have for how many different books could I place in each position? So here's first on my shelf, here's second on my shelf, third, 4, 5, 6, 7, 8, 9, 10. 10th on my shelf. Last on the shelf. Okay, so if I've got 10 books, how many possibilities are there for how many books I could put first on my shelf? Well, clearly I could put any book first on my shelf, so I've got 10 possibilities, 10 options for which book goes first. Okay, how many options do I have for which book goes second? Well, once I've put one of the books on the shelf, I can't also put that book second. So now I've only got 9 options left for which book could go second. How many options do I have for which book could go third? I hope you said 8. This is just like the dessert example. So once I've placed these 2 books, now there's only 8 choices left for the third position. And then 7, and then 6, and then 5, 4, 3, 2. And then once I've placed 9 of my books, I only have 1 book left over, and I only have 1 position left over to put it into. So for the last position, I have 1 choice, the only book I have left. So as I said in the last video, a shorthand way of notating 10 times 9 times 8 all the way down to 1 is 10 exclamation mark, where the exclamation mark is called factorial. So you'd call this 10 factorial. How big is that? That is 3,628,800, which might seem large. That's a very large number of different ways you could put 10 things in order. And that's one of the exciting things for me about combinatorics is the space of possibilities gets so large so quickly. There's a lot of really important problems in computer science that involve trying to look at in a search space. You're trying to find the solution to something, and you're testing out all the possible solutions. But the number of possible solutions you have to test out is, many orders of magnitude larger than the size of the the number of particles in the observable universe. It's like, search spaces get gigantic even for very small human-sized problems. Okay, so back to permutations. If I want to know how many different orders could I put 10 books on my shelf, the answer is 10 factorial. If I ask you how many different orders could I put 12 books on my shelf? 12 factorial for the same reason. You could work this out as a fundamental counting principle kind of a problem, but hopefully you see the pattern is going to end up as 12 factorial. What if I want to give awards for the most honorable student in pre-calc honors? Let's say we've got 36 students, and I want to give a first and a second and a third place award. How many possibilities are there? The answer is not 36 factorial, because I'm not putting 36 students in order. If I wanted to rank order the 36 students as being first most honorable, second most honorable, third most honorable, and so on, that would be putting 36 students in an order, and there would be 36 factorial ways to do that. But in this one, I'm still putting students in an order, because I'm still choosing a first and a second and a third. So if I chose Bill and Carlo and Sally, choosing Bill, Carlo, Sally is really different than if I chose Sally, Carlo, Bill. Because in this situation, Sally is probably happier because she got first most honorable, whereas here she got third most honorable. So the ordering does matter. if I'm giving a first and a second and a third place. It's just that I'm only ordering 3 students instead of 36. So hopefully you can imagine how this works as a box problem, as a fundamental counting principle. So here's first place, second place, third place. How many options do I have for my first place student? Could be any of them, 36. How many options do I have for my second place student? 35, because I can't give the first place student second place, so they're out of the running. How many options do I have for my third place student? 34 options left. So one way of writing this down that's common in combinatorics is I'd say 36 factorial divided by 33 factorial. Let's think about for a second why that makes sense. 36 factorial is going to be 36 times 35 times 34 times 33 times 32 times 31, and so on off the screen. Okay, what's 33 factorial? That's 33 times 32 times 31 times 30, and so on off the screen. Look at what cancels. 33 cancels with 33, 32, 32, 31, 31, 30, 30, all the way down to 1. So what I'm left over with is 36 times 35 times 34. So that's the idea, is if you have a factorial that you want to kind of cut off at a certain point, you're just going to divide by a smaller factorial that will cancel all of the smaller terms.